Nick Wu is going to talk to us about effective programming. Nick.
Great, thanks for the invite. Yeah, so I'm here to talk about effective programming, and I want to just start with what the problem is. So here's the problem. There's a company called GitHub. They're quite big. We've all heard of them. They've got 40 million developers that use their software, and they host 100 million repositories. And they're fed up of just hosting repositories. They actually want to do something interesting with this stuff, namely allow their users to learn about their code. So, for instance, if you've got JavaScript and you want to know how many lines of code you've got, then some poor engineer has to fill in the green tick and implement that for you. And they also need to do things like code navigation, and so somebody else has to come along and do that work as well. And then, of course, there's more than just JavaScript. You also have things like PHP, and so lots more work needs to be done. And the thing I want to stress here is every single one of these green ticks represents work. And before you know it, you've got more features and more languages that you need to deal with. And so if there's one thing that we should know about code in the wild is that code explodes. And here we have a kind of complexity explosion where we've got just too much work to do. So this thing has completely exploded. It's been a catastrophe. And so the technical challenges that GitHub wanted to deal with really were that this whole system needs to be robust, and in the sense that the structure of the problem should inform the structure of the solution. It needs to be modular in the sense that you need multiple syntax with multiple semantics. It needs to be comprehensive in the sense that you need support for lots of different programming language constructs, and it needs to be efficient because they're dealing with millions of repositories. And it turns out that my research was a perfect fit for solving this problem. So what I gave these guys was a kind of one ring to rule them all approach, where I gave them a way of talking about syntax in a modular way and talking about semantics in a modular way, and combine these things into what's known as a domain-specific language, which combines the advantages of general-purpose languages and domain-specific ones as well. So the theory of all of this comes from what's known as recursion schemes. And a recursion scheme I like to think of as a kind of railroad track for your code. It makes your code predictable, and that predictability allows optimizations to kick in. And we've all seen recursion schemes because we teach them to our first years. So this is like folding lists. So a list is like 2718, which you can decompose into either the empty list or consing things on. And then if you want to take the sum of this list, you would replace your empty list with 0, you would replace your cons with pluses, and then we call this a fold. So is this thing useful? Well, yes, these things are useful for not just adding things up, but you can also do things like you can multiply, you can take them in. And the point is that the structure is very, very predictable. And so you can do this thing called fusion, which allows you to replace multiple passes of your data with a single pass. Google uses this with their MapReduce strategies for parallelism. In practice, we don't care too much about lists. We care about things like trees. So you can do the same trick with trees and replace the nodes with addition or multiplication or min or whatever you like. And for GitHub, they don't care about trees so much, but abstract syntax trees, which of course cover syntax itself. And that's the sort of syntax and semantics idea that I gave them earlier on. So this maintains nice calculational properties, and it leads to optimizations like fusion, and is based on decades of research. And in fact, because it's theoretical, of course, we give it silly names like the catamorphism is what we call this recursion scheme, and it belongs to a whole zoo of different morphisms. And some of my work was to basically show that this zoo is all part of a single unifying theory called a so-called conjugate hylomorphism. And I won't have time to go into detail there, but roughly speaking, there's some nice theory. So effect handlers is why I'm calling it effective programming, because what we really want is a kind of layer-by-layer approach to syntax for GitHub's problem. So we've got the syntax and semantics, and rather than trees, we represent things as what is known as a free monad, which is the thing on the left-hand side. And that's basically a syntax tree, where the yellow things are the leaves and the green things are the nodes. And you can give different semantics, and you can sort of do this railroading, as I suggested earlier. So the conversation went something like this with GitHub. We met in a conference, and they said, oh, sorry, I forgot to say, effect handlers, as I've discussed, have been implemented in lots of different languages. So Frank, F, and Lynx are more obscure ones, but it's also been implemented in Clojure, F#, Scala, C, Haskell, OCaml, and JavaScript. And big companies like Uber have invented their own. So Uber invented Pyro, Microsoft made Coca, and Facebook made React. So GitHub came along and thought this might be a good solution to what they were looking at. And so they thought, well, the trouble is that algebraic effects don't work with all syntactic constructs of languages. So it doesn't work for if statements and try-catch. So they chatted to me, and I said, well, it looks like what you need is these things called scoped effects that I've been working on. So I gave them some papers to read, which they did diligently. And I explained to them that all you need to do is add a syntactic construct that allows you to talk about certain kinds of constructs in a more specialized way. And this was based on some interesting category theory with some really gnarly proofs, but they didn't need to understand any of that. The implementation just worked fine. So they implemented it, but they were worried that it might not be efficient. And so I told them about fusion in another paper, which basically says, given lots more theory, you can show how this stuff becomes very, very efficient. And so they implemented that, and things were 250 times faster than their previous attempts that didn't cover all language features. They rolled it out into production. And so now every time anybody pushes any code in Java, JavaScript, C#, Python, PHP, it's executing code that's based on my work that basically does the code analysis in an effective way. And so obviously people on Twitter were quite excited about this. And that's the beginnings of effective programming. So I'll stop there. Thanks for the invite.